to the next speaker. I'm Maarja Kruusmaa. I'm a professor of robotics, and I come from Tallinn University of Technology, which is right on the outskirts of this town here in the campus. And actually, I'm a professor of IT and robotics and sensorics. So what we do for our research is that we build different things to understand what's going in parts of the world where people have not been able to gather information before that. So we define ourselves often that if you've never been in a place something like that and never got information, so if we can build you gadgets where you can go to places where you've never been before and you never got information. Thank you. Just few of the examples here, for example, is a little underwater robot that goes inside of the shipwreck where it's very hard and very dangerous to go. Or here is a little gadget, what we'll later tell we can also deploy in Svalbard, but we first developed in order to understand river hydrodynamics. Or here is, for example, a robot which is developed for going inside of abundant caves and abundant mines underground. And it looks funny because these little things around it is to emulate a touch sense, because there is very little information down there, and it can by touching understand where it is. Or we have different sensors that we later talk about Svalbard, but also they eventually, in the beginning, they developed in order to understand the river and coastal hydrodynamics here in Estonia or in Central Europe, and then we understood we can also study them elsewhere. But yes, we praise ourselves for actually doing some innovation, technological innovation, but the innovation is often oriented towards having a very rugged, very fault-tolerant, very deployable sensors that are very resilient in different environments. And as you maybe understood from there, we mostly do underwater technologies. So going underwater is difficult already. People think that the hardest thing is to going deep on the bottom of the ocean, but it's often not so. It's often so that, for example, coastal regions here in Estonia are much more inaccessible because they are very turbid, dynamic, there is a lot of sediment and things like that. And you also have to make little things in order to go into a shallow water. So shallow might be more difficult than go into a deep water. But also even harder than that if you start going out of the water, but you're still not on a dry land. So you're going somewhere like a mud and sediments, and we talk a little bit about that too, that being in those muddy places could be even more difficult. But now you could already understand why we are actually so fascinated about Arctic, is that you probably maybe know the saying that if something works in Arctic, it works everywhere. So it's probably natural for us to go into these places. Once we got a test case that this works there, we can easily go to tropical islands and say, well, this is like already showcased in Arctic, and it works. And Arctic also, we know that you already heard from the previous speakers, there is a lot of changes now going on in Arctic, and we need more data to understand what are the effects of the climate change, how much of the climate change do we have, and to forecast all that. And for that we need data. And there is a peculiar thing with an environmental data. It's kind of things to be that way that if you already have a lot of data, then you go and sample more data from places where you already have data. But you still have the data gaps from places where are very hard to go. And for example, if we have satellite data, we can record data from a surfaces, from an earth surface, from a sea surface. But if you go under the surface, it's much harder to get data. And for example, you can have some sensors somewhere under the surface, but this just gives you one measurement point. It doesn't cover the whole area. So there are big areas of Arctic and Antarctic where you simply have no data at all because there are no technology, or it's too expensive, in order to go there and gather the data. And similar is going to the bottom of the ocean, is going under ice, same thing, and also polar night. Just deployment, recovery, but also if satellites, optical satellites not working in a talks, then you again have a data gap. And in order to fill this data gap, it's not just building devices, but it means like you have to build rugged devices that will endure the whole polar night, for example, and the other things that are inexpensive enough you can actually afford having those devices. And that's also a very big thing. And finally, as the previous speaker said in the end, that what scientists really want to see is long time series. And well, long, it depends what is long. Sometimes long is a week because it's so hard to measure things, but sometimes it's years or sometimes it's decades, but the longer the better, right? So what we need is long time series, but we would also like to have a nice spatial resolution. If you have like one data point, one sensor somewhere in the middle of the polar sea, that just gives you one measurement, but you would maybe want to have 100 and you don't have them. So I present you two cases where we in Arctic try to get data from places where you normally don't have data from. And the first one is a glacial meltwater path. We already saw in a previous slide how glaciers are retreating. We try to understand the glacial dynamics. Why are they retreating so fast? Are they going to retreat faster? Are there any threat in places where also humans are living, because glacial retreat might make the glacier unstable? And for that, we need a lot of measurement from the surface of the glacier, with seismic sensors, with lubrication of the glacier, with the bed of the mountain, and so on, to understand the dynamics of the glacier. So from where we often don't have any data at all, we never have any data at all, is a glacial meltwater path. What happens inside the glacier when the glacier is melting? So in summers, the glacier is always melting. There are going to be these little tracks of meltwater, like little rivers appearing on a bed of the glacier or the surface of the glacier. And then at few points, this water is just disappearing because it's falling into big holes, moraines inside of the glacier. And then basically nobody knows what's happened before this water comes out from the other part. And between this part, when it goes inside of the crevasses and coming out from the outlet of the glacier, it's basically unknown what's happening. And what actually happens there, we sometimes get a glimpse when we go there, like in the middle of winter, or if the channel is really big, it looks like the big water slides in a water park. So there's a lot of water going with incredible speed, and you can imagine how much energy is in that, and all this energy is going inside of the glacier. Definitely changes the dynamic of the glacier. So from a point of view of understanding how the glacier is behaving, it's also important to understand what the water is doing inside of the glacier. So our answer to that, as we are technology people, we build gadgets, was that, well, we build gadgets. And we put the gadgets inside of the glacier, and then we thought that if we let them flow or drift with the water and some gadgets, and we understand what are these things actually recording. And this is a little sensor which actually contains a accelerometer and a compass and a pressure sensors. And if you see it's going with the flow, and here you could also see that it measures, for example, in this case, pressure. And after a while, when it just keeps watching the whole thing going, then you can see that, if there is, for example, a pump in the channel, it suddenly falls, and you could actually see also a pressure drop somewhere, and you could see it from the acceleration. Or when there is a very lot of turbulence, it behaves differently. And finally, if you're watching those things for a very long time, you start understanding the nature of the channel, what is this water actually doing, sir, just by looking at this data. But that's not enough, because this is a description, right? You know, you could look and say, okay, there should be a little waterfall, but you can't really like quantify the thing. So what you actually need is to take the signal and then analyze it mathematically to understand what's happening to that, to have a quantitative description of the glacial meltwater pathway. And we thought, of course, it's a easy thing to do, so we went to Svalbard and we actually ended up working like 5 summers or something. Not all of them were equally successful. We first thought that it's not a big thing, we just drop our things into the channel and so go to the outlet of the glacier, and then we just wait, and then the things are coming up. And then we catch those things, and then we read the data, and then we start analyzing the data. I go, for some reason it's not working anymore. Okay, but you know, you can imagine, it's funny, it's working here. Let me see, let me fiddle around a little bit, maybe I get the video working. No, not, unfortunately, you can't see the video. Oh yeah, you can see the video, yeah. At least the beginning of it. So, yes, it worked, yeah, it worked out in some years, and some years it didn't, because we lost all our sensors. In some years we caught the sensors. We ended up developing it further and further, because we understand that once you drop somewhere in Arctic, and finding it is very unlikely in the end, that you have to be very very fortunate to find your things. First 2 years we got very good data from New Orleans, from a nearby glacier, Östra Bukebren, where we find a very nice channel and we drop our things in, and then we found at least like 70% of all the sensors we dropped in. Then we went to Kongsvägen, and there was a big glacial lake burst, and we tried to investigate that for 2 summers, but we mostly lost all of our sensors. And since the sensors went to Austfonna with a research ship, and we got very nice data from there as well. So having all this data means that in the end, once the field work is done, it's a lot of work already, but actually for us, this is where the work begins, because now we're sitting on the top of like hundreds of gigabytes of data, and we have to do something with that. And that's basically what we start with, is developing mathematical algorithms, taking all these sensor information, the signals, and understanding what is happening. And that's actually is maybe not so obvious, but this is actually where robotics comes to play, because it's a very standard problem in robots. You don't know when you are, and you have to find your way, and you have to localize yourself when you're a robot. And you don't have a global reference, you don't have a GPS, which you don't have in a meltwater channel. So first GPS point is when you drop something in, and the second GPS point is when you take it out. And between those points, you actually don't know where you are. And what we then do is that we apply machine learning algorithms to make a probabilistic reasoning. What is the most likely path which we are taking with those sensors? And especially if we have many sensors going and there are similarities, then we could take that this path is more likely than the other path. So we never know for certain, but we are certain that we are completely wrong neither. So this is a nice thing with the probabilities, that we are also, it's probably that to some degree you're still right. And in this little video here you can see a reconstruction of a glacial meltwater channel in Östra Bukebren in New Orleans, and the colors there indicate the pressure. So it's sometimes it's more pressure, sometimes it's less pressure, which is also, and you could also have the same for acceleration. So these are all kind of a indication how much energy the meltwater water puts into the glacier and changes dynamics of the glacier. Pressurized glaciers are specifically interesting. We never had a chance to investigate them because we always lost all our things. But sometimes the pressure inside of the glacier becomes very, very large, and that could even lift the glacier up from the bed of the mountain and just simply put it into a different place. So these are the places where the glacier becomes unstable and are extremely important and interesting to investigate, what we also would like to do in the future. But so far we have some good glimpses into the places where nobody have got data before from inside of the glacial meltwater pathways. So this is one data gap that we probably have been able to fill in with our technologies. And the next one I would like to tell you is about investigating coastal dynamics in ice fjord and in Svalbard for the last 2 years with Rico Normets, who is also a speaker, and he fills you in more with all the scientific background, why and how to study coastal dynamics. As I said, we are mostly the people who provide here the technology, and this is, I think, for say first Estonian financed polar campaign during the Estonian Republic, our new independence now, where we can do Svalbard and financed by Ministry of Foreign Affairs, were sent to go there and deploy our sensors and then later recover those sensors. We still all look happy there because we just had a very successful deployment, and we were hoping coming back a year later and understanding better the coastal dynamics. So what's added value with this technology is that if you take this place here with this ice fjord and the little branches of the ice fjord in here and look at it with a Copernicus, since that would be just probably one data point on a satellite data. So you get just one point understanding. This is, for example, on June 24th, this was the speed of the height of the waves and the speed of the winds or something like that. But actually within that region, the speeds and wave action and currents, they vary a lot, but we cannot see it with the resolution that the satellite is giving us. And this is now where we're coming to the data gaps. If we want to have to understand with a better resolution what is actually going on in a fjord like that, then we need more than one data point. We need many data points at the same time, and as a previous speaker was also emphasizing, preferably we should measure for a very long time to understand what is actually happening. And here are different deployment points that we have in different branches of the ice fjord. And first year we deployed 9 sensors, we recovered 6, we were very happy, we thought that this is a very good recovery rate. Everybody who works in Arctic knows it's a very good recovery rate. And this year we were back in Svalbard and we were looking for our 6 sensors left and we recovered 0, so this wasn't that good recovery rate. But anyway, we ended up with a very good data for the whole year's period, which is quite unique on this sort of resolution. And from a technology point of view, there's actually one more thing to emphasize, is that doing polar research costs a lot of money, like a lot of money, and equipment costs a lot of money. But in this case, also the cost of the sensor was not very high. It was actually quite cheap. So we mostly regretted not losing the sensors, but losing the data. And it's also a way of making polar research more affordable. If you have cheap sensors, you can deploy them, many of them, and then you can also afford losing something without bankrupting your research team. So that is a good thing. Here is now our sensors put on the seabed, and this is the sensors, which is recovered a year later. It has a little kind of rod on the top of the sensors here. So the innovation here is that we can measure without acoustics. We can measure mechanically the wave action and currents. What happens is the water moves, then the stem here starts vibrating, and from the vibrations of the stem, we can actually figure out what is a speed of the current and what is the direction of the current, and also what is cycles of the wave action. So here, for example, you could see a longer measurement period, and here, if you zoom in, you can also see that within like 1 day and one sensors, how actually the signals, the flow velocities in this case, changing like with tides and currents and with the wave action. And of course, what you actually, if you're a physical oceanographer, what we'd actually want to have is what you call a high energy event. So what actually makes very many changes on a coastal region are the storms. But it's very hard to go to the coastal region and to say, oh, the storm is coming, I'm putting my sensor in there, and when the storm has gone, then I go and take it out. So it normally doesn't work that way. But you need to have something that works reliably, works for a very long time. You put it there, and then it just sits, and then it just waits, and waits until the storm is coming and starts recording, or records all the time, it doesn't matter. But what you're really interested in are the high energy events. So you want to understand what is actually happening, there's a lot of energy around the coastal regions. And why is it important? Also, the next speakers are going to talk about is that if you have a lot of energy in the coastal areas, then the sediments are replaced, and how it exactly happens, you have to make an interconnection between the sediment analysis and bathymetry analysis. How is the coast and how is the bathymetry, the coastal bottom profile of the base, and then match it to the sensor data of the wave action and the action of the current, which gives the possibility to understand and to model how the sediments are moving. But also when you're able to model, then you also know that you can predict how the sediments are going to move in the future. And in this case, why it's important in those areas of Svalbard is that Longyearbyen is the biggest inhabitant of Svalbard. So what happens in Adventfjord really matters to people who live there. There is a little community, but really if the coast is changing with the climate change, they need to know that. And this kind of a measurements give actually understanding what is happening to their homes with the climate change. But now if you zoom out to the whole Arctic, and there are a lot of many settlements like that, for example in Greenland and Svalbard and north of Norway, mainland Norway and elsewhere, lots of things are happening. So you can think of that if I have now this very high resolution understanding how the glaciers are providing more sediments, how the sediments are moving, how the storms are changing, how the direction of winds are perhaps changing, and I'm able to model it, then I could also be able to be prepared to the climate change for the local communities in the Arctic. So these are now the next things we are going to look very closely to the data that we have gathered and understand and predict what is happening in Adventfjord and maybe also elsewhere in the future. So just to cap it up is I think that there is a lot of that technology could provide to help data gathering. It's not just making more sensors, but it also means like making more innovative technologies, different kind of technologies that were not there before, in order to measure cheaper and more reliably and with a better resolution. And I've talked a lot about deployment or recovery, because this is, what we've been doing and takes a lot of energy. But actually, we also understand how important is everything to do with the data management, and all the polar researchers have a lot of work there to do, a lot of work here to harmonize the data, to work on the protocols, to work on the standards of the data, so that one data collected by one researcher is findable and usable by the other researcher, and so on. But even more, in our research group, we also work on pipelining the data. If we take data from a place like these glaciers, and it takes us about a year to process that data, which is very little, because when Amundsen went to the North Pole, it took 20 years for him to go later on through all of his notes and actually publish those things. So things are actually moving faster. It did like 100 years ago or so, but what we would like to do ideally is that when you come home from your polar expedition, or somebody else gathers from data, your paper, so to speak, is already almost ready, because all the data processing, pre-processing, filtering, modeling, predictions is all automated. It takes very little time. And right now it's not the case. Very often it's not a case. It takes very long time, and the data quality is a very big concern. And I also think that, coming myself from a background of IT, and I know in Estonia there are a lot of people who have a good experience already and a lot of expertise in data handling, data processing. There is actually a very good research gaps that we could fill in with this data automation, data processing technologies. And since I also can say that if we find those gaps, which at the moment are crucial, then small nations might have a much bigger role to play in polar research that would have been anticipated by their size, because if we could bring to the polar research exactly those little missing building blocks to better understand and better predict the climate change. With that, I would thank you for listening to me, and if there are any questions, I would be really happy to answer.
Kadri and Dam, Department of Energy Technology, and I'm very happy to see that my university colleagues have done fantastic work. But I still have a question about sensors, and the loss is quite high, and there's still somewhere. Is it that possible they still collect data?
Mm-hmm. Yes, they probably do, because we've had cases in New Orleans that somebody found our sensors a year later in New Orleans, just on a coastline, and the SD card was all intact, so we could read out data. So it's the question is finding it.
But still, is that data is also losses, or you still put it in your mathematical models, or?
We could probably retrospectively do that. Yes. Mm-hmm. Yes.
Mm-hmm. Okay, that's good news.
Yeah.
Mm-hmm.
Yeah. Thank you.